Nature is governed by four fundamental interactions: gravity, electromagnetism, the weak interaction, and the strong interaction. The one that we're interested in is a strong interaction, and the theory behind it is called quantum chromodynamics, or QCD. With only two ingredients, quarks and gluons, QCD tries to explain a wide range of phenomena, from the collisions taking place at CERN with very high energy, to how the protons and neutrons are squeezed together to form the nucleus of the atoms with very small energy. The problem is that, while for the first case we can manage to understand the process using pen and paper, for the second one it is very difficult, since all our mathematical tools break down at this energy regime. If we want to use QCD directly to compute, for example, how the mass of the proton emerges from the interaction between quarks and gluons, the only way to do it is by using computers, or, to be more precise, supercomputers. We need to put QCD in a computer. The way to do it is by using lattice QCD. It has the word lattice in it because what we do is discretize the spacetime in a four-dimensional grid, placing the quarks on the nodes of this lattice and the gluons on the links. But why is it so computationally demanding? We have to evaluate the path integral, or in other words, we have to compute every possible path that the quark can take from one point of the lattice to another. This is done by solving the following linear system, where D contains all the information about the interaction between quarks and gluons, called the Dirac matrix, X is what we're trying to get, called the quark propagator, and B is the right-hand side vector, which tells us where we put the quark on the lattice, called the source. Naively, one would have the temptation to solve this problem by just inverting D. But if I tell you that the Dirac matrix is a huge matrix with a lot of elements equal to 0, computing the inverse is not an easy task. Therefore, it is crucial that we use a method that can handle this type of problems. One of these methods is the multigrid solver. The multigrid solver can be thought as a combination of different algorithms, with the main purpose of speeding up the convergence of iterative methods. And the way it achieves it is by projecting the initial system into a smaller one, which should be faster to solve. Without going into too much detail, the solver proceeds as follows. Starting at the original lattice, the initial guess of the solution and the real one are very different, so we do a few steps with an iterative solver. This is called smoothing the solution. Once it is smooth enough, we project our solution into a coarser lattice. Here, we can do the same as the previous steps, or if the new lattice is small enough, we can try to find the exact solution. With an exact solution, we have to project it back to the original lattice. Since now we have to stretch it, we have to do a few more steps with the iterative solver to make sure we still have the solution for the linear system. How can we make this solver faster? Well, this is where vectorization comes into play. When coding, it is very common to see the following loop. One would think that the CPU does each operation of the loop at a time. First compute C0, then C1, etc. But modern CPUs are much more intelligent. Since CPUs aren't getting any faster, what engineers have come up with was to increase the number of bits that the CPUs can process at a time, called registers. If instead of having registers of 64 bits and processing one double precision float variable, we can have registers of 128 bits, or even bigger, and process two variables at a time. There are two ways of vectorizing a code, an explicit way and an implicit way. The explicit way requires the use of special functions, while the implicit way, which is the way we chose, is to prepare the loops in such a way that the computer knows they can be vectorized. So, what was my project about? The original goal was to vectorize the whole multigrid algorithm, so that instead of solving the linear system for one right-hand side vector, it could do it for two or more vectors at the same time. But after preparing the code, so that we could put the loops over the right-hand side vector in the right place, we decided that we should begin by modifying the iterative solver used in the multigrid method, the generalized minimal residual method, and see if it worked. Here are the results. In the upper part of the plot, there is the time it takes to get the solution of the linear system, using the normal solver or the vectorized solver, as we increase the number of right-hand side vectors. And in the lower part, there is the speed that we obtain by vectorizing. As we increase the number of right-hand side vectors, we reach a value of 2, which is the ideal speedup. The reason we don't get it right away is because the compiler puts a lot of if statements to make sure that it uses the right amount of data inside the registers, and they clearly slow it down. The next step is to solve this handicap and then get the whole multigrid solver vectorized.